In this video, we're going to talk about the derivatives of logarithmic functions. So we're going to start with the basic logarithm, the natural logarithm, finding the derivative of y equals ln of x. Now pretend, if you've seen this before, pretend you've never seen before. So how do we find the derivative of something that we have never seen before? Normally, we rely on the definition of the derivative, right? That f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, for this particular one, it will be the limit as h goes to 0 of ln of x plus h. So I'm going to have the natural log of x plus h minus the natural log of x, right, minus my f of x, all over h. But the problem with the definition here is that we do not have a property of logarithms that tells us how to split up a sum. So this cannot be simplified. And so we can't use the definition of the derivative here. So what we're going to do instead is we're going to use implicit differentiation to find the derivative.
So how do we use implicit differentiation to find the derivative here? Well, we're going to lean back on the definition of the logarithm. So I know y equals ln of x. This really means the base of the log is log base e. So I'm going to say this is log base e of x. In using the definition of a logarithm, what do I know about the definition? Is that if I have log base b of a equals x, this can be rewritten, right, one way or the other, so forwards and backwards, as b to the x equals a. So that means that this, using my definition of logarithms, can be rewritten as the base is e, so e to the, what's on the other side? So e to the y equals the a, what's on the inside of the log. In this case, the inside of the log is the x. And so I can rewrite my natural log of x as e to the y equals x. And this is why e and ln of x are inverses of each other. So now I can take the derivative with respect to x, right? I want to find the derivative of the function with respect to x. So find, essentially what I'm doing is taking the derivative of y with respect to the variable x. And now notice that e to the y, right, think of it as e to the f of x, or my super technical notation, e to the stuff, right? So how do you take the derivative of e to the stuff? Is you get the exponential back, e to the stuff times the derivative of the stuff. So when I take the derivative here, I'm going to have the derivative of e to the y will be e to the y times the derivative of y, which is y prime, equals the derivative of x with respect to x is just 1, and solve for y prime. Right, we're trying to find the derivative, the y prime. So that means divide both sides by e to the y. And so I'm going to be left with then y prime equals 1 over e to the y, right? But what was e to the y? E to the y is really just x, changing it back to what it was. So therefore y prime is 1 over e to the y, but recall, right, e to the y is equal to x based on our definition of the logarithm. So this is just 1 over x. So what this means is that for f of x equals to the natural log of x, then f prime of x is 1 over x. And so now we have the derivative of the natural logarithm function. So let's try an example using what we just found. So here's my example. Find the derivative of x equals cosecant x plus 2x to the third plus ln of x. So we already know how to find the derivatives of these other things, but now we're introducing the natural log of x. So what is the derivative here? f prime of x then is going to be the derivative of cosecant. What's the derivative of cosecant? That's negative cosecant x cotangent x plus the derivative of 2x to the third will be 6x squared using the general power rule. Now plus the derivative of natural log of x is, we just found out to be 1 over x, and so this will be my derivative. So let me recap. Then we have for f of x equals ln of x, the derivative is 1 over x. Now what about including chain rule here? So if I have f of x of the natural log of stuff, my very technical notation here, what do you think the derivative is going to be? So the derivative of f of natural log of stuff is going to be, right, derivative of natural log of x is 1 over x. So whatever is inside the logarithm, that becomes the denominator. So then this is going to be 1 over the stuff, but then by chain rule times the derivative of the stuff. I guess I shouldn't say ddx because our variable may not be x. So I'm just going to say times stuff prime. And this is by the chain rule. So let's try another example. Let's try this example that requires us to use the chain rule. So find dy dt. So notice the variable, the independent variable now is t. So that means y is a function of t. So y equals ln of t squared plus 1. So using the chain rule, then my derivative here is going to be dy dt is equal to, I have ln of stuff, so it'll be 1 over the stuff, t squared plus 1, times the derivative, in this case with respect to t, of the stuff. So what do I get? So this is going to be 1 over t squared plus 1 times 2t, the derivative of that, and so we can simplify it to be 2t over t squared plus 1. You may see in your book that the way that is written is that if you have, so I'm going to rewrite my functions. For f of x equals ln of x, f prime is equal to, right, 1 over x. But then if you have, for let's say f of x equals ln of g of x, then the derivative is, right, that's the stuff, is going to be 1 over the stuff, so 1 over g of x times the derivative of g of x. So we're just going to write it on the numerator. So g prime, the derivative of the inside in the numerator, and then whatever the inside is in the denominator. So back to that one function where I said y equals the natural log of t squared plus 1, I could have said dy dt is, take the derivative of the inside, so that's 2t, and then the t squared plus 1. Sometimes this just seems like, where did it come from? And so that's, but that came from here when you have the chain rule. I prefer to do it to show my steps, that is 1 over the stuff times the derivative of the stuff, and then simplify it, just so that it is more clear what exactly is happening, right? Is the derivative of ln of something, ln of stuff is 1 over the stuff, so I see the y, the t squared plus 1 went to the denominator, and then times the derivative of the numerator, like, oh, okay, so then that's why it's that. So, but this is what you may see in the book, right? Ln of a function is the derivative of the inside function divided by the function that's on the inside. So either way is okay. I just want you to be aware of both. All right, let's try another example with a more complicated chain rule. So for this example, we're asked to find the derivative of g of x equals ln of that stuff. And so that looks like I'm going to have to use the quotient rule, right? So then my derivative, g prime of x, is going to be ln of stuff. So derivative of ln of stuff is 1 over the stuff. So I'm going to have 1 over x squared plus 1 over 3x minus 7. And then times the derivative. So now my variable is x, so the dx of x squared plus 1 over 3x minus 7. And so here, what rule do we have to use? I have a quotient, right? So we're going to use the quotient rule. I see a big division there. So so 1 over this fraction, so it's really the reciprocal of this fraction, so let me write that. So I get the reciprocal times now the derivative of this. Using the quotient rule, it will be the bottom, so 3x minus 7 times the derivative of the top, so times 2x, quotient rule, so minus the top left alone, times the derivative of the bottom. The derivative of 3x minus 7 is just 3 all over the bottom square, the bottom of this, my 3x minus 7 square. So that is the chain rule. I mean the quotient rule, and and the chain rule within that logarithm. So let's simplify the inside. So I'm going to have 3x minus 7 over here over x squared plus 1 times, and then let's try to simplify the inside. The reason I'm putting this in parentheses is I can already see that maybe I can reduce that 3x minus 7 with one of those 3x minus 7s. So right, I'm going to be able to say this divided by this cancels one of them out, and I'm going to have a 1 over here. But let's work on the inside here. Let's see, multiply, there's only one term here to bring in, so 6x squared minus 14x, and then bring in the 3 and distribute that negative, so minus 3x squared minus 3. And again, I simplify some more. Yes, so now that's gone, so I just have 1 over x squared plus 1 times, let's see, 6x squared minus 3x squared is 3x squared minus 4x minus 3 all over, one of those went away, so I still have 3x minus 7. And can we do anything else? Okay, that's this factor. Two numbers that multiply to negative 9 and add up to negative 4. That's not going to work. And so, no. So that's as far as we can go. So I'm just going to leave it then as 3x squared minus 4x minus 3, right? That numerator times that numerator divided by that denominator times that denominator. X squared plus 1 times 3x minus 7. Phew. And so that is the derivative of g of x. So that will be g prime of x. So that seemed more complicated than maybe we like, right? But notice that some of you may be thinking, Professor, why did you do it that way? Isn't there an easier way to do it? Yes, there is an easier way to do it, and is by bringing in the properties of logarithms, because notice I have the natural log of x squared plus 1 divided by 3x minus 7. So there is a property of logarithms that we can use to rewrite our function. So let's review the properties of logarithms real quick, and then we'll redo this problem using the properties of logarithms. All right, so the rules, the first rule is if you have the product of two things inside a logarithm of a particular base, then you can say this is the log base b of x plus the log base b of y. And then the quotient rule for logarithms is when they're being divided, you can subtract them. So it becomes log base b of x minus log base b of y. So we're expanding, right? So for my single logarithm, you expand into the sum of two logarithms when the inside is multiplied. When the inside is divided, you take that single logarithm and expand it into the difference of two logarithms. Here when you have a power, so this becomes, you can bring the power to the front. So it's y times log base b b of x. Now this one we have to be careful. We are bringing the power to the front because it's a property of logarithms. Oftentimes as we take derivatives, right, we have the general power rule where we bring the power to the front. So oftentimes some of us confuse the rule of logarithms with the general power rule, and what I see is people bringing the power down and then subtracting 1 from here. Be careful, that's not what's happening when you're using the property of logarithms. Is the property of logarithms, not the general power rule. And log base b of b, that's just 1, right? The extension of this is if you have log base b of b to the x, you just get x. All right, so back to that function, we had that g of x was the natural log of quantity x squared plus 1 over 3x minus 7. And the way we did it first was using the rule of logs with the chain rule, that the derivative of ln of stuff is 1 over the stuff times the derivative of that stuff. But in taking the derivative of this stuff, I have to use the quotient rule. So that lets me know that, oh, wait a minute, if I have to use product rule or quotient rule and I have a logarithm, I can probably rewrite it using my rules of logarithms. So here we're going to use the quotient rule of logarithms. I guess I shouldn't call it the quotient rule because it makes it sound like the quotient rule of derivatives, but it is the quotient property of logarithms. So we're going to then rewrite it as the natural log of the numerator minus the natural log of the denominator. So rewriting g of x, notice that I am not taking the derivative. I'm just rewriting using properties of logarithms. So this becomes the natural log of the numerator minus the natural log of the denominator. And now can I do anything else? No. So now I take the derivative. And so when I take the derivative, I have g prime of x. I still need the chain rule. So ln of stuff, that's going to be 1 over the stuff times the derivative of the inside, so times 2x minus 1 over the stuff times the derivative of the stuff. And so my derivative then is 2x over x squared plus 1 minus 3 over 3x minus 7. So notice that how much easier this was to do than what we did over here. 1 over the stuff times the derivative of the stuff made it really complicated because I had a quotient rule there and I had to do all that work. Are they the same answer? They probably are. They should be. It's just that here everything is combined. So if you get a common denominator, we should get the same answers. So if you get a common denominator, what does that mean? That means multiply this by 3x minus 7, top and bottom, and then multiply this one by x squared plus 1, top and bottom. And I'm doing this just to show that they are the same answer. On a problem, you don't have to combine them. So this will give me my 6x squared minus 14x. So notice that those numbers are starting to look familiar. So minus 3x squared minus 3 over my common denominator. And so notice that we are doing the same math that we did when we did the quotient rule. So 6x squared minus 3x squared is 3x squared minus 14x minus 3 over that common denominator. Is it the same as what we got before? Yes. Oh yeah, that should be a 14. Good thing I came back to it. Would have left that mistake on the video. 14. I did say 7 times 2 is 14, but I wrote 4. So are they the same answer? Yes, they are. But which one was easier to do? Rewriting it. Using the properties of logarithms to rewrite it makes it a lot easier. So let's try another example where we get to rewrite a problem. Now for this example, find f prime of x for f of x equals ln of x to the 7th e to the cosine x. So you may be asking yourself, like, how do I know when I rewrite or when I just take the derivative? If I just take the derivative right now, I will say f prime of x is 1 over the stuff times the derivative of the stuff. But when I take the derivative here of x to the 7th times e to the cosine x, what do I have to do? There's a reason I said x to the 7th times e to the cosine x, right? There's this a product, so I have to use the product rule. So anytime that I find myself that I need the product rule or the quotient rule when doing the chain rule on a logarithmic problem, that means that I can rewrite it. So I'm gonna pause there and stop myself and be like, oh, wait a minute, I can rewrite f of x using properties of logarithms. So f of x here is going to be, because this is a product, x to the 7th times e to the cosine x, I can use the first rule of logarithms, that the product of a single logarithm becomes the sum of two logarithms. So this will be natural log of x to the 7th plus the natural log of e to the cosine x. And notice that with this one, we can even go further. So we're using the first rule, right? The product becomes the sum of two logarithms, but now I also have powers. So when I have log base b of x to a power, I can bring that power to the front, which is what I have here. I have x to the 7th and I have e to the cosine of x. So rewrite some more. So this is going to be f of x is then bring that power to the front 7 times the ln of x. And this is where I'm saying be careful, right? This 7 is coming to the front because it's a property of logarithms, not because I'm using any sort of derivatives yet. Plus, natural log is the log base e, so I have log base e of e to the cosine, so that's just cosine x. And now, can I use any more rules of logarithms? No, that's as far as we can go, so now I can take the derivative. So f prime of x will be 7 times the natural log of x, which is 1 over x, the derivative of natural log of x, plus the derivative of cosine, which the derivative of cosine is negative sine x. And so that will be our derivative. So 7 over x minus sine x, and you can just leave it like that. If you want to get a common denominator, that's fine. Write that over 1 and then do x over x, but you don't have to. So notice how much nicer it is to use the properties of logarithms than having to use a product rule or a quotient rule. So I guess the issue would be if you don't remember your properties of logarithms, then rewriting it is harder. And if you are pretty good at your product rule and quotient rule and the chain rule, then you might choose to do the chain rule and do that big product rule. But rewriting it is a much shorter and cleaner way of doing this problem. We'll do, on part 2 of this video, we'll do more derivatives involving logarithms and slightly harder ones. All right.